Okay, let's start today's session. Welcome to week 10 of problem solving sessions for analog electronic circuits. And this week's content is basically mostly based on the frequency response of the analog circuits that you have dealt with so far. So till now you have seen analog circuits with DC, only with memory-less elements. That comprises of your transconductors, your resistors. But now, we will see the frequency. Like in this week, we have saw this week and mostly previous week also we saw frequency effects in transistors when we have parasitic capacitances in the circuit. And particularly in this week, we saw that how multiple amplifiers in a loop can somehow create instability in the loop when there is a delay in the system. So we studied all about that. So before we delve into problems of this week, does anyone has any doubt in the course content so far?
Yes, sir.
Okay,
Sir, problem
yeah,
number 3, week 9.
problem number three, week eight,
Week 9.
week nine, problem number three. Okay, let me pull it off. Uh, so let me see that. You can see my screen,
Yes,
right? So this is the problem number three. Is this the problem that you are talking about?
yes, sir. Sir,
Yeah.
here
So
only one side VI is given input. So
sorry.
incrementally,
Yeah, yeah.
only one side input is given, not
Correct.
sequentially, not given both sides. So when
Yeah.
I'm drawing incremental, then that whole current mirror circuit it goes away. But that node at put of 16 transistor is I don't know what its voltage is.
Uh,
Eight,
just
eight,
a minute.
eight, very, very,
Just a minute. Let me take this circuit to my iPad and then we will discuss. Now I hope my uh, tablet screen is visible to you, my
yes,
workspace. Yeah.
yes.
So can you please repeat your doubt?
Sir, in drawing small signal model, how do we know
Yeah,
that this node has no small signal? First I did Vi is equal to 0, then found all the percent voltages. After
correct.
then I start drawing small signal model. But during that I have doubt that the transistor with 1 W by L, its drain is it swinging or not? And 8 the transistor with W by L 8 its drain is swinging or not.
Uh, so
So
okay. So let's try to decode what circuit is this. So let's say this connection was not there. What this circuit would look like? So it's basically we have uh, 50 microamp current over here that is being mirrored using this PMOS current mirror. So this is 4, this is 8. Here, let's say some VCM is put, VCM plus VI. Let's say this VI is not here, and we have put VCM on both the sides of the transistor. Okay.
Yes.
So now can you tell me what kind of circuit is this? So what is the function of this current mirror? How much will be the current that will be flowing through this? Let's label the transistors also: M1, M2, M3, M4, M5, and M6. Okay. So can you tell me what is the current that will be flowing through transistor M2?
100.
100 microamp. And if basically if I have a VCM on gate of transistor M4 also, so 50 microamp will be flowing through this, and 50 microamp will be flowing through this. You understand this?
Yes.
Yeah. So what is this structure? This complete structure. What is the structure?
It's like
Sorry, your voice is not clear. Can you please type? I think the reason you might be getting confused is so you have seen the differential, the standard differential to single-ended structure with NMOS input pair and PMOS load. So that basically looks like this. So it's basically an inverted, this is an inverted stuff. So here you have PMOS load and NMOS input pair. NMOS load and PMOS input pair. So this is basically a differential to single-ended op-amp, five transistor, standard five transistor differential to single-ended op-amp. So now what is if let's say both the RON, in the is there some lambda or some this thing? Is there some lambda given for these two transistors in the question?
no, sir. Zero. Zero.
No lambda, right? So what will be the gain of this differential to single-ended structure?
GMR
Yeah, so RO is infinite. So what will be the gain?
is an infinite.
Infinite. So the gain will be infinite. Okay. Now, how you can view it as, so since it's a differential to single-ended structure, right? So basically what you have is how does your op-amp look? Like if you make it if you make your op-amp in like a model, uh, block model, so basically this is how you make it, right? So you have two terminals, VOP, VOM, and your output, VIP, VIM, and your Vout, correct?
Yes.
Yeah, so basically, to realize this structure, you can use this five transistor structure, right? It has two inputs and a single output, correct?
Correct.
So, can you tell me which out of the gate of transistor M3 and M4 will be the negative terminal and which will be the positive terminal? So how will you go about deciding that? So let's say I give a small signal positive voltage on gate of transistor M3. What will happen?
The current increase,
Current will
increase,
current will increase. Are you sure?
no decrease because it's P0.
Because its VGS is decreasing, right?
Yes,
Its VGS is decreasing, so current will reduce. So if this current has reduced, what will be, and this is the output, VOP. So what will be this current, the current through transistor M6?
It will reduce, sir.
Yeah, this will also reduce.
yes,
Now,
yes,
what is happening is more current is being pumped into this node VOP because this is still maintained at same. More current is being pumped into this node VOP and less current is being pulled out of this node VOP. So what will happen to this the voltage of the node VOP?
increase.
This will increase. So if you are increasing this, increasing the voltage on this terminal, VOP is increasing. So your gate of transistor M3
Plus,
is plus terminal and gate of transistor M4 is minus terminal. Okay, so plus and minus. So what will happen is now you tell me that okay. So how will you make uh, an non-inverting amplifier using this op amp?
give input at plus and feedback take minus. Output connect to input.
Sorry, this is minus and this is plus. So how will you connect what terminal will you connect?
Negative terminal connect with P0.
Negative terminal connect to V naught and give input at Vi,
Yes,
correct?
yes,
So if you want to make the similar the same thing using the real transistor, which two nodes you will have to connect?
VOP and VCM.
The gate of transistor, the VOP you will have to connect by gate of which transistor?
And so,
M4, right? So this is what is asked in your question, right?
yes,
So basically, you are giving input to the positive terminal and giving output, taking output at the negative terminal. And this structure is a high gain structure and is connected in negative feedback. Okay. Now, so let's say while doing the large signal analysis, when Vi is equal to 0, the negative terminal, the negative feedback of this structure will ensure that both the node, the let's call this node B, both node B and node A are at same voltage.
yes, yes.
Why it will happen?
Due to DC negative.
Sorry,
Due to feedback negative.
due to feedback. Okay, so this node, like the negative feedback mechanism will make sure that this node is also fixed at VCM. Okay, do you understand?
Yes,
Yeah. Can you tell me what happens if this node, let's say, goes to VCM plus some delta V? What will happen now? What will happen to the current that is flowing through this transistor?
same current will flow 50 micro.
Sorry. So let's call this node is A. What will happen? The current that is being pushed into the node A. If this has increased by delta V, The current will increase or
decrease,
decrease? The current will decrease. So the
decrease,
current that is being pushed into the node A has decreased. So what will happen to the voltage of node A?
decrease.
It will decrease. So basically, if let's say due to some disturbance, if the voltage at this node is trying to go up, the negative feedback mechanism will basically make sure that it comes back to the original value of VCM. Do you understand?
Yes,
Okay, so so whatever VCM you apply in large signal, till the time this all the transistor the VCM is in the range such that all your transistors are in saturation, your node A will also remain at VCM. Okay,
yes, sir.
so do you understand how to solve this problem?
Yes, sir. Sir, in BCM, finding the common mode range is asking, then how to go about that? From above, I should take, or from below, VT
That's
and
what
plus
you
2
should
delta.
find both like maximum and minimum. So when it says range, so you should find that what is the maximum it can go, what is the VC. So basically, none of the within the range that you are finding, none of your transistors should go out of saturation. So what you should do is when the VCM is increasing, which transistor can likely go out of saturation?
The below
Sorry.
one, the NMOS one,
Okay, I will label
because
the transistor. Can you tell me which one? So if VCM is increasing, which
M,
transistor?
M5,
M2. Which one did you say?
M5,
M5. Why? Why do you think so?
the drain of M3 decrease and VGD of M5 increase. But
Uh,
that's
dr-
zero. That's okay.
See, when VCM is reducing, both the when you are actually reducing the common mode, this is the large signal, this thing that you are reducing. So both VCM of B and VCM of A both will go up. Okay, when you are increasing the VCM. So, and if both are going up, the current that is flowing through both the transistor is unaltered. So in that case, these drains won't have any impact on them. That's what your common mode rejection ratio is, right? The no matter how much you change VCM, your drain side won't be affected.
Yes,
So now can you tell me which node will, let's say, so there is a fixed current that of 100 microampere that is flowing through transistor M8, correct?
yes, sir.
And if this is fixed, that means to say as long as transistors M3 and M4 are in saturation, 50 microamp will flow through transistor M3 and 50 microamp will flow through transistor M4, correct?
Correct.
So their VGS of transistor M3 and M4 are fixed. Why? Because the current through these transistors is fixed,
Yes,
correct? So what will be this node?
sir.
VCM plus
Plus delta V
V,
plus.
VSG 4.
Yes,
You understand?
yes, yes, sir.
Okay. So if I'm increasing VCM, this node is increasing, right?
Yes, sir.
And if this node is increasing, your transistor M2's drain is basically increasing, and it can increase only to a point where the drain is at least one threshold above the gate of transistor M2.
Yes, sir. From
So
there we can find BCM.
in there you can
Yes.
find the upper limit of VCM. Now, what will you do to find the now, when the VCM keeps on reducing, which transistor can go out of saturation?
M6, sir.
Is there any other transistor also that has risk of going out of saturation? One
M3
candidate is
and
M6,
yeah,
other candidate
M3.
is M3. Can you explain me why M6 will go out of saturation?
Sir, because of a drain voltage. If a drain voltage is getting reduced,
Correct.
M6
So,
will.
VCM is basically the voltage at node VA, and this is also the drain voltage of transistor M6. So, as it keeps on reducing, it can just go one VT below the VGS of transistor M6. So that's how M6 can go out of saturation. Other possibility is that this node. The drain of transistor M3 is basically fixed at VGS of transistor M5. And since this node is fixed and the gate of transistor M6 is keep on reducing, so the transistor M3 might go out of saturation if this VCM goes 1 VT below the VGS of transistor M3, sorry, M5. So the two constraints, the two likely possible candidates for that can go out of that can determine the lower minimum range of VCM is one is basically VCM going VCM should be always greater than or equal to VGS 6 minus VT. Other candidate is VCM should be greater than or equal to, this is
Yes.
VTN. VGS and VGS 6 and VGS 5 are equal, right?
Yes.
So VGS 5 plus VTP. Okay, you understand this?
Yes, sir.
So which is the larger quantity?
Below BGS 5.
The below, this is the larger quantity. This is modulus of VTP. VTP is actually a negative quantity, but here we will have a modulus of VTP. So VCM. This is the larger quantity, and this will make the this will ensure the lower limit of VCM, lower range of VCM. So basically, as the VCM keeps on reducing, before the M6 goes out of saturation, M3 will go out of saturation. Is it clear?
Yes, sir.
Okay. Any other doubt?
No, sir.
Okay. Anyone else has any doubt? Help us, right? All clear till this point.
Yes, sir. Yes, sir.
Okay. Let's see some concepts in that we have learned in week 10. So, can you tell me what concepts have we learned in week 10?
Sir, two-stage compensation, Miller
Compensation.
compensation
And Miller
band gap
compensation
difference.
is done, is it? I
Yes, sir.
think right now it's only the dominant pole compensation, or Miller compensation has also been done.
I mean, sir, I gone through every video, sir.
Okay,
Dominant problem. Dominant problem.
let's try to,
Sir, it is possible to band gap difference, sir, starting.
sorry,
Band gap difference, sir.
Do you have any doubt in band gap reference?
No, sir. Any numericals if you solve, I will get a summary.
So, okay. So, can you tell me what kind of numerical you want to see on band gap reference? I mean, do you have any specific numerical that you have doubt on?
No, sir. In general, you will teach, no, sir, from what is importance of band gap, and then you
So,
will do complex.
okay, let's see that way. How is the basic band gap reference generator formed? So, basically, we have one diode, and this is, let's say, 1x diode, and this is, let's say, an NX diode. So, what do we do over here? What we want basically is so this NX, so this 1x diode voltage will be varying with minus 2 millivolt per Kelvin, like kind of slope, and we want to compensate it. So what we do is we basically make sure that these two voltages are equal. So we try to create a current that is having a positive temperature coefficient. So how do we do it? We basically want a current source, the PTAT current source. So and here we take the output. So what we do is we make sure that what is this voltage?
V out, sir.
Sorry. So this is basically VBE, and the current that flows over here is and this V out is basically I times, let's call this R1, let's call this R2. So I times R1 plus VBE. Wait, I think I have done a mistake in this. Sorry. Mm, this is VBE. Can you guys help me draw the basic band gap structure?
Yes, sir.
So this is R2, and this is connected like this. And where do we take the output?
Drain side, sir.
Which
Source.
drain?
Drain, sir. That will MPM PMOS
And this is
2, sir.
M1, M2.
Yeah.
What is the output of this band gap reference generator?
Mm. I into R2 plus VB, sir.
No, which node is the output? Which node will be the which node will have the which node will have a temperature coefficient 0? like which has that possibility. What is the voltage at this node? This node is
Yeah. So okay. Sir, N into VB here with left side is VB.
left side is VB and right side will also be V. First of all, help me find the direction of the currents in the direction of the terminals in the op amp.
Yes, sir.
Okay, how will you go about finding the direction of the terminals of the op amp
Sir, based on the output,
based on output of what?
based on the op amp output, we can decide
Okay,
input.
can we we did this exercise, right? To find out the negative, to find out the feedback, the direction of the op amp to ensure the circuit in negative feedback. What will you do is you will basically cut the loop at some high impedance node. Is this node a high impedance node?
No,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Okay. So if we cut the node over here, let's call this voltage as V test. Now, which of these two voltages will be higher? Okay. What will be the sign at node one and node two? If this is
Uh,
V test, this is a small signal voltage.
yes, sir. Left side MOSFET one diode, no. Right side many diodes. So uh, the right side will be inverting, sir.
No,
Non
no,
inverting.
forget about inverting and non-inverting. Just tell me that if this is VT,
Hmm.
and let's call this some alpha VT, and this let's call this some beta VT. Okay.
Hmm.
So what will be the signs of alpha and beta? That's what I'm asking.
Okay.
What kind of architecture is this?
PMOS load op amp. PMOS.
No, no. See, I have disconnected this. Now I am giving the input at the gate of the PMOS, and so I am asking that if let's say this was to behave as an amplifier,
Common
what
source.
kind? Correct, common source. Now, what is the sign of output of input to output of common source?
Minus.
Yeah, minus. And what kind of architecture is this?
Common source.
Both of them are common source. So both of them will have negative sign. Correct?
Yes, sir.
Okay. Now, tell me which one will be larger? Will the gain from node O to 2 will be higher, or gain from node O to 1 will be higher?
Sir, note 2 because of more diodes.
Sorry,
Note 2, sir.
node 2. What will be the gain from let's say these transistors M1 and M2 have infinite resistance output resistance. What and the GM of both the transistors is same of GM. What is the gain from node O to 2?
It should be infinite only, no?
Why?
Because output resistance is infinite, no sir.
How?
If output resistance infinite,
The
need
output resistance of transistor M2 is infinite, but what is the total resistance that you see at this node, node 2?
it is R2.
R2 plus.
Diode resistance are small r.
So basically, your gain from like AO2 is equal to minus of GM times R2 plus R by N. Okay, RBE by N. What is AO1?
Yes, sir. Minus minus GM and RB, sir.
RBE. Okay, which is the smaller gain?
Definitely R A02.
A02 is smaller.
No, 01.
N will increase, no sir.
No, no, that is okay, but what is the value roughly the like this when the diode is forward bias its resistance approaches zero, right?
Yes, sir. Ideal case.
Okay, ideal case and approaches the zero. I am saying like it will be very small resistance. So compared to a actual physical resistance, its value will be very small.
Yes, sir. A01
Okay.
will be
Okay,
less.
so your A01 will be a very small value and A02 will be a very high negative value. So which terminal should be the positive, which terminal should be the negative terminal?
Terminal 1, sir.
Why? You want
Because
negative feedback,
gain
right?
is very less, right?
Yeah, so you want negative feedback, negative feedback. So terminal one should be negative. That's what you are saying.
Yes, sir. If it increase,
So if let's say your our O has increased, your this will be reducing largely, and this will be reducing with a small quantity. Okay, you understand?
sorry, sir.
I can
Repeat it.
disagree.
Yeah. So basically, this has already inverted. So both node 1 and node 2 are already inverted, and you want that inversion to come over here also. So since node 2 is inverting higher, so this should not face any further inversion. This would be positive, and node 1 should be negative. Okay.
Sir, how, sir? Node 2 because of gain or
Yeah, because beta VT, okay, more like absolute value of beta VT will be higher than alpha VT. You agree with this?
yes, sir.
Okay, and beta VT is actually a negative quantity. So, the final output over here, if you call this some VTO, VTO will be basically VTO, you want to be a negative quantity, and beta VT is already a high negative quantity, while alpha VT is a smaller negative quantity. So, if you have over here beta VT minus alpha VT, will this be a negative quantity or a positive quantity?
Yeah, positive, sir.
Why?
So beta VT,
Negative.
Beta VT is a negative quantity, is a higher negative quantity. So like beta VT minus alpha VT, minus alpha VT will become a positive quantity. And but since beta VT is higher than alpha VT, so overall beta VT minus alpha VT will be a negative quantity.
Yes, sir.
Yeah. So that's why you want no inversion on beta VT side and you want inversion on alpha VT side. So this is the direction of the op amp.
Sir, so beta VT, so already gain is in more. Alpha VT, if you take inversion, the gain will inversion will change, right? Anyway,
Yeah.
output would be inverted only, right?
Which output?
Op amp output, sir.
Yeah, op amp for the op amp output to be inverted, beta VT should not face any inversion, while alpha VT should face inversion. Because beta VT and alpha VT both are negative quantity. So the one which has higher feedback factor or which has higher gain should be kept non-inverting.
Yes, sir.
Okay. So that's why the one on side of beta VT is positive and the one on side of alpha VT is negative.
Okay, sir. The net resultant will be negative only, no?
Yeah, the net resultant is negative when you have positive on node 2 and negative on node 1.
Hmm.
And that's what you want.
Yes, sir.
Okay.
Yes, sir. Continues.
Okay. So, what is the mechanism of achieving like a constant voltage across temperature? This will basically vary with a negative temperature coefficient. Wait a second. So basically, the transistor, the voltage across the diode will vary with negative temperature coefficient, and the voltage across R1 will vary with positive temperature coefficient. So their addition, and we will add that, and if we specifically choose R1 and R2 to make its slope also equal to -2 millivolt per Kelvin, you will get a constant voltage at the node V out. Let's call this V out. So this is how a basic band gap reference circuit works.
Fine, sir.
Okay.
Sir, if you could you please tell me how to calculate that R1 and R2, make sure this band gap 2 millivolts.
So it's straightforward only, no? And this has been taught in class. So uh, what is the actual current? Can you help me find out the actual current?
Yes, sir. V out minus VB by R1.
V out minus VBE by R1. Okay. Now, what is V out then? I'm you need to find out the current without V out. So in terms of all other circuit components. So what is the voltage at node 2? Voltage at node 2 is VB only, right? Because of virtual short of op amp, correct?
Yes, sir. But there is will be drop on R2, right?
Yeah, there will be drop on R2, but the positive and negative terminals of the op amp have to be at the same voltage, right?
Yes, sir.
So if this is VBE, this node will also be VBE,
Hmm.
correct?
Yes, sir.
And due to the current mirror, since VGS of transistors M1 and M2 is same, the current flowing in like both the branches is same. So if the current flowing through current flowing through 1x diode makes the voltage VB, what will the current flowing through this NX diode make the voltage at this node VB by N, right?
Yes, sir.
Okay. So now you know this is VB, this is VB by N. So your actual voltage is VB into 1 minus 1 by N. Correct?
Yes, sir.
Okay. Divided by R2. So this is your current. Sorry, it won't be VB by N. What it will be? VB by basically both the currents are same, like I1 and I2 are same. So what is I1? It's basically Is into e to the power VBE by VT,
Mm.
and I2 is basically N times Is into e to the power VBE2 by VT. And since both of them are equal, so you will equate I1 and I2. So what you get is e power VBE by VT is equal to N times e power VBE2 by VT. So what you get? VBE2 as
Sir, ln of 1 by n.
ln of 1 by n
Hmm.
times,
VB1 by
no,
VT. Yeah, VB1 by VT into
ln
VT, sir.
of 1 by
VB.
n times VT plus, sorry, my plus, yeah, plus VBE. Wait, uh, we have VB2 minus VB over here. It's so 1 by n is equal to e to the power VBE2 minus VBE divided by VT. So yeah, correct. So this is what you get as VB2. That is this node, correct? This
Yes,
is
sir.
VB plus or VB minus VT ln of n, right?
Yes, sir.
Okay. So what is the voltage different voltage across this resistance R2?
Yes, sir. I into R2,
VT
sir.
ln n,
Yeah.
correct? So VT ln n, and if this is VT ln n, the current will be VT ln n n by R2, and the same current will be replicated over here. So you will have the voltage across R1 will be VR1 will be R1 by R2 times KT by Q. KT by Q is basically your VT times ln of n. Okay. So your V out will be VBE plus R1 by R2 times K by Q of ln of n times temperature. Okay. So this is basically a positive quantity if n is greater than 1. This is a positive quantity. And this will have a so basically if you differentiate it with respect to temperature, you get this as minus 2 millivolt per Kelvin, and this you get as R1 by R2 into K
PT, sir.
by Q times ln. Okay,
Sir,
okay.
because by adding this, we get a proportionality later.
Yeah, this should be equal to,
PTAT.
huh?
Proportionality, no, sir.
No, no. I am talking about the differentiation of complete output voltage. So this
Sir,
should be
before,
equal to zero, right? You want your output voltage not to vary with temperature.
yes, sir, sir. Previously, it
Okay.
would be complementary. By
Yeah, it's
adding this,
complementary, you know. This
hmm,
is basically the VBE's differentiation is minus 2 millivolt per Kelvin, and your PTAT, this is your PTAT voltage.
hmm,
This is your CTAT voltage,
CTAT.
right?
Yes,
Okay,
sir.
CTAT is minus 2 millivolt per Kelvin. Your PTAT is R1 by R2 times K. What is K?
Hmm.
What is K?
Uh, Boltzmann constant.
Boltzmann constant divided by Q, that is the charge of the electron, into
Yeah.
ln ln of n. And K by Q, you can remember, you can find
26
out
millivolts.
not 26 millivolts, it's 26 millivolt divided by 300 Kelvin. So 26 millivolt, 26 into 10 to the power minus 3 divided by 300.
Hmm.
Okay, and now you basically have these many design choices. You can basically choose the ratio of R1 by R2, and you can choose like the N. If you have a very large N, then you don't. Ln N times R1 by R2, you should choose in such a way that overall this quantity becomes equal to 2 millivolt per Kelvin.
Yes, sir.
Okay,
Sir, but
and yeah.
when circuit is in executing now, at that time we cannot change it. How can we do at the time?
I couldn't understand your question.
Sir, for example, CTAT it is two millivolts per kilo. If it
Correct.
is changing, no, sir, uh, 10 millivolts, accordingly will change. But it is temperature is continuous, no. So at that time, every time we cannot go and
No,
design, no,
no.
sir.
The temperature. So your assumption is that your VBE falls linearly with temperature. So temperature is continuously falling, changing, but the slope of the voltage versus temperature is constant. That's what you assume in this circuit.
Yes, sir. Yes, sir.
Okay, which is actually not true because see, we assume that VB basically does this thing. VB, if this is VB, this is temperature. We assume that it will behave like this, and its slope will be basically minus 2 millivolt per Kelvin. But in actual practice, it does something like this. Okay. So when you actually, but this on the other hand is linear in true sense. Okay, but this is basically varying this is like somewhat deviating from linearity. So the actual band gap voltage that you get V out with temperature is in ideal scenario you should have got a completely flat curve, but you actually get something like this. Okay.
Yes, sir.
So basically what you are doing was that earlier it was varying by this much amount. Now it's only varying by this much amount.
Yes, sir.
Okay.
Sir,
There is some, yeah.
hmm. Sir, fixed GM and band gap in fixed gym also, can we design band gap, sir?
No, no, fixed GM and band gap are two different things. In fixed GM, basically what fixed GM circuit does is fixed GM circuit basically changes the current of the transistor in such a way that across PVT, its GM remains constant. That is a different concept.
Okay.
This is fixed
So could
voltage.
you
That is fixed GM.
please elaborate a little bit, sir? In an interview also told, so it would be helpful.
So basically fixed GM, so let's say there is some black box that basically provides you with a voltage. Okay. So, and if this is a fixed GM circuit, what it and you apply it to some a transistor like this, so it will basically adjust its so its voltage will be a variable voltage which will adjust itself such that the GM of this circuit remains constant. So let's say if the mobility is increasing due to temperature, the mobility mu n is increasing. In that case, this voltage will reduce itself to keep the GM constant. If the mobility is reducing, this voltage, this GM will increase itself to keep the GM constant. That's how a fixed GM circuit works.
Yes, sir.
Okay. While on other hand, if you give it with a fixed with a band gap reference generator, band gap reference generator will give you only fixed voltage. So your VGS will be fixed always, but your GM will keep on varying based on the temperature.
Yes, sir. Yes. Yeah.
Okay. Do you understand this?
Yes, sir. Yes, sir. Perfect.
So, one of the drawbacks of the circuit is, what is your VB? Okay, before we go into that, so can you tell me how will you decide I will shed some light on how do we decide the value of N and R1 and R2 in practice? So this N typically in band gap reference generators is kept as 8, and the reason behind this is ease of layout. So you guys are familiar with the term layout, right? Schematic and layout.
Yes, sir.
Everyone? Okay. Some of you guys are not. So basically, what the complete IC design process goes in this way. So first of all, you get a PDK. Let's say PDK. What is PDK? PDK is a process design kit that will have information about mobility of transistors, the threshold voltages of the transistors, the lambda of the transistors, and so on. Okay. So based on this PDK, you will use the model of the transistor to first of all design, let's say, a circuit in schematic. So let's say you are designing let's say you have a diode. You are designing the diode with BJT and you design it like this. So this is a schematic design. Now, so this is basically 1x design, and this basically, so like n of these you connect with each other. So this is your nx design. Okay. So this is basically a schematic representation of BJT. Layout is basically the representation in the fashion how it will actually look on a silicon. So let's say this particular layer will so you know how integrated circuits are made, right? They are planar circuits. You understand this? Okay. So let's say this basically looks like a square. This BJT in practice, like in physical form, it looks like a square when looking from the top. Okay. Let's say this complete sheet of paper is the silicon, And when you look from the top, it looks like a square. Okay, this is a 1x BJT. Okay, so this is basically layout of this transistor. For this thing, how will it look? It will basically look like 8 of such squares connected with each other. You understand? Okay, so in layout, basically what you want is you want symmetry in layout, that whenever you actually make a circuit, you want that circuit to be symmetric both by x-axis and y-axis. So to have that symmetry, what you want, generally the value of n is chosen as 8. Why it is chosen as 8 is, so you will place the 1x transistor in between, and you will place the 8x transistor along it. So let's call this transistor M1, this transistor M2. So you will place M1 in between, and M2 you will place like this. M2, and this is M2. So what is it? The M2 is basically a replica of 8 such M1. You understand this? Okay, so what this will help you do is, so this is now symmetric both around x-axis and y-axis. So 8 is a convenient number which makes your layout look symmetric. So generally your value of n is taken as 8. And why you need this to be symmetric is, let's say there is some temperature gradient. So temperature here, or let's say the process of making silicon might be such that here temperature is, let's say, T1, here temperature is T2. So like M2 will face an average temperature of T1 plus T2. That will be around this thing, and same temperature will be faced by a transistor M1. So you want that environment, the centroid of both this M1 and M2 to be same. That centroid of both of them in this case lies at the origin. uh, it's a little tough to visualize without like proper background of it, but I hope I'm making a little bit of sense over here. Okay, so this kind of symmetry you generally want in layout. So like a typical number to use in band gap reference generator is 8. So that's why so if this is fixed to 8, and KT by K by Q value, you know, that comes out to be 26 millivolt by 300 Kelvin, and you can find out your R1 and R2 accordingly. You understand?
Yes, sir.
Okay. So
Sir, for every time we need to substitute
yeah,
n equal 8 only, sir.
yeah. In this particular example, you need to substitute your value of n to be 8.
Will they mention n take this value?
No, no. I mean,
Like
see, as far as your problems in your exam is concerned, they can mention any value. It can be 8, it can be 16, they can mention any value. But like when you actually design, you typically keep it as 8. There might be other designs also, but yeah, this is a common practice.
yes, sir. Thanks.
Okay. Now, one of the drawback with this so basically, as you mentioned, 26 millivolt by 300 Kelvin is, I don't think it's zero point 0, it's 0.086 into 10 to the power minus 3. Yeah. So this value, you know, know the value of 8, and the ln of 8 is basically 3 times ln of 2, and ln of 2 I think is around zero point 0.3. So ln of 8 will be zero point 0.9, and you know K by Q now, you know ln of 8, and that this multiplied by R1 by R2 is equal to 2 millivolt per Kelvin. So from there you can find out the ratio of R1 and R2, R1 by R2. Now, as far as finding individual R1 and R2 is concerned, there are several other things that you should take care of. So, like depending on how will you find out what resistance value you need? Uh, can anyone explain me? So, let's say I choose a very small value of resistance. What will happen?
Based on the voltage, you will choose the value auto.
No, no. The voltage is fixed. Whatever R1, R2 you choose, like whatever absolute value of R1, R2 you choose, it's fixed. Voltage cannot change. It's around 1.2 volts, like if you remember from your class. So, what is the current that is flowing through this particular circuit? It's two times Vt ln n. It's two times Vt ln n by R2, right? The current. Vt ln n by R2 in each branch. Do you understand this? Okay, so if you, let's say, choose a very small value of R2, what will happen is the current consumption of this circuit will increase very much. And so you always need to reduce the power consumption of current that a particular circuit is drawing. Why? Because if the current consumption is very high, then your battery will drain very easily. Okay, so you need to choose a reasonably large value of R2. If you keep on increasing the value of R2, then your physical realization of R2 might not be feasible. So you need to choose the minimum value, maximum value of R2 that is possible in your technology to make the band gap reference generator. You understand? And once you choose the value of R2, your value of R1 gets fixed based on the formula that, based on the principle of band gap reference generator.
Sir, first R2 value should be fixed, right?
Yeah, R2 value should be fixed based on whatever maximum feasible
Okay.
resistance is available in your technology, and then uh, once that is fixed, you can choose the value of R1 based on the ratio that you require.
Yes. Sir, could you suggest me any books for band gap reference pro?
These circuits don't exactly come in I can't remember a book for this thing. Wait, I will look it up and tell you. I think Razavi might be having this. Can you just check?
Analog ACDC.
Yeah, I'm not sure though. You can check whether Razavi has this. If Razavi has, it's okay. Otherwise, I will get back to you, like which book you can refer to.
Yeah, 11th chapter, sir. 376.
Okay. So now one of the drawback. Okay, one more doubt is there. In differential pair with active load, Sir said PMOS load has characteristic in first and third quadrant. So even though it's called active load, it is passive. I didn't get this statement. We call it active. You know that any element, if has the IV characteristic in first and first and fourth quadrant, it's second and fourth quadrant, it's a active element in, and any stuff that has uh, the IV characteristic in first and third quadrant, it's a passive component. Do you know about this?
Yes, sir. Based on that graph, we will decide. Na?
So, so if basically
That's,
you
if
have
passive element means the slope should be
just a minute,
positive, sir.
just a minute. So basically we have V is equal to IR, right? If
Yes, sir.
voltage is on this side and current is on this side, what will happen is, let's say it goes something like this. Okay, that means to say, power at any time. The power dissipated by a device is basically the product of voltage and the current. That product of the voltage developed across that device and the current that is flowing through that device. That is the power that is being dissipated. So if you are
Yes,
in
sir.
first quadrant or the third quadrant, the power that is being dissipated by this device, the product will be always positive. Okay. So if a circuit, if a element is dissipating power, it's a passive element. However, if your characteristic looks something like this, in that case, the power dissipated will be negative. Okay. So if the power dissipated is negative, that means it's supplying power. So that particular circuit is a positive, active circuit. You understand?
Yes, sir.
Okay. Now, as far as your this particular circuit is concerned, there is VDD. So if this is the according to passive sign convention, your if this is your voltage, let's say some voltage V developed at this, let's call this VGS. In that case, your current should flow inside. The passive current, according to passive sign convention, if this is VGS, this is positive node, your current should flow inside uh, inside the voltage source, or inside the positive terminal. Okay. Now, this is basically your VDD minus VGS. Okay. And current is flowing inside this. So VDD minus VGS, as the current increases, just a minute. So your VDD minus VGS is a positive quantity, right?
Yes, sir.
Okay. If VDD minus VGS is a positive quantity, that means it will lie in the positive quadrant, on the upper half of the Cartesian coordinate, and your current flowing inside, if let's say is positive, that means to say your VDD minus VGS will basically vary something like this, correct?
Yes, sir.
More precisely, it will vary like this.
Sir, but current should be negative. No, for PMOS.
Sorry. Yeah, correct. It basically varies like this. Correct.
Yes, sir.
Initially, so like consider the uh, if you consider the small signal like large signal equivalent of the circuit actually lies in the third quadrant, the second quadrant. So it basically is as far as large signal equivalent is
Active.
concerned, it's indeed an active circuit. But if you see only the incremental change, incrementally, what will it look like? For example, something
Yeah,
around
1
this
by
thing.
GM, sir.
It's
With
basically doing
uniform
this
source
thing
code.
with a slope of 1 by Gm. Okay. So as far as small signal is concerned, this is a passive circuit, but as far as large signal is concerned, this is an active circuit.
Yes, sir.
Okay. Now let's see one drawback of this particular band gap reference generator. So we say that this output voltage is 1.2 volts or 1.25 volts, something like that. Correct?
Yes, sir.
Okay, if this is 1.2 volts, what should be your power supply?
Yeah, it should be V out minus VGS equal to 1.2, sir.
So basically 1.2 plus VGS P minus VT P, correct?
Yes, sir.
Okay. So one overdrive above your 1.2 volts, correct? So the power supply has to be very high for this circuit to work.
Yes, sir.
Okay. Now, let's say I want to make a band gap reference circuit where I need the low power supply. What will I do? Have you guys studied the concept of fractional band gap circuit?
Uh, no, sir. No, sir.
Okay. So let's say I need to reduce the voltage. Let's say the power supply is limited. Let's say I have only 0.8 volt power supply in my chip. So this
Yeah, VDD,
circuit
sir.
cannot work, right?
Yes, sir.
Okay. What is basically limiting me in this particular case?
Overdrive voltage, sir.
No, overdrive voltage I can reduce. I can reduce this overdrive. I can make these transistors size very large, and I can make the overdrive voltage of these transistors very low. That I can reduce. What I can't reduce? I can't reduce this 1.2 volts, right? This is a device
Uh,
characteristic you get from
yes, sir.
device only. Okay.
Hmm.
So, the problem is that we are adding voltages. Okay. And how we are adding voltages? By stacking two voltage sources on top of each other, right?
Yes, sir.
Due to
Cascade.
which stacking.
Cascade.
So I am keeping a VBE, and on top of the VBE, I am putting one more resistor and adding two voltages by stacking the voltages. Okay.
Yes, sir.
Now, like instead of adding voltages, if I add currents, so there this kind of additional headroom I won't be needing, right?
Sorry, sir.
So, like instead of adding the voltages, if I add the currents, I won't be needing this kind of additional headroom. Do you understand?
Yes, sir.
Okay, like my main problem is that I am adding this VBE and then I'm adding a PTAT voltage. Okay, so here I get PTAT plus CTAT, and this voltage becomes very high, so I have a bottleneck on the power supply reduction of the circuit. This is the problem statement. You understand the problem statement? Okay, so instead of this, if I do this thing, there is some resistance PTAT and CTAT. I will need only so much voltage that I can make sure that these two current sources work in a saturation region. The volt amount of power supply required will be reduced significantly. And CTAT plus PTAT I am adding. So here instead of a band gap voltage, I will get a like a constant
Correct.
current across temperature. You understand?
Yes,
Okay.
sir.
So we'll try to make this circuit. And okay, so let's try that. So we have VBE over here. This was negative, this was positive. R2, this is NX stuff. The only reason I needed a resistor over here is because I wanted to add a PTAT voltage on top of VB. Let's say I don't want that. That means to say I don't need this resistor over here. So I can directly connect it to this thing and still this stuff will work. Okay. Let's say I have something like this now. Okay. Now this is VB. What is this voltage? VBE minus VT ln N. So what is this current? This current is
VB, VTLN
VT
by.
ln N by R2, or now let's call this R. Okay. So this we got as PTAT current.
Yes, sir.
Okay. Now we need to generate CTAT current. How will we
The
generate
CTAT,
that?
CTAT will be present, sir, in general.
Where?
No, because of CTAT only we are applying PTAT, right?
I couldn't understand what did you want to say.
Sir, if it is complementary current is there, then only we are making PTAT to make zero, sir.
Okay, what will be your PTAT current? What will be your CTAT current? Will VBE by R, assuming R is constant, Any diode drop divided by resistance will give CTAT current. Correct. Okay.
Yes, sir. Yes.
So what I can do is, if let's say I have a resistance over here, okay, just a minute. So this current will be VB by R, right?
Yes, sir.
Correct. So if we have VB by R over here, that means to say this is the CTAT current, and this is your PTAT current. Okay. Now just a minute. So how we can add it is, mm, so let's say I have this thing. Give me a minute. So we have generated CTAT and PTAT currents. We need to add it somehow. Let's say how we can do that. Or if we have the resistance over here. Okay. Let's say we put the resistance over here, this R value. Okay. Now, what will be the current in this? This will be your VT ln N by R. The current in this will be VBE by R. Correct? Okay. So what will be this current? 1 by R times VBE plus VT ln N. Correct? You understand? So here we have added CTAT and PTAT current. Now let's say if we want to generate a voltage out of this particular current, what we will do is we will take another current mirror and place it to some value R1. Okay. So what will be the current that will be flowing? This will be the same current and this current. I1 and I2 will be same, right? So if I1 and I2 are same, that means to say the voltage that is developed, let's call this V out. Our V out will be R1 by R times VBE plus VT ln of N. Now, if we choose R1 to be smaller than R, we can basically generate a constant voltage across temperature that will be R1 by R times 1.25 or 1.2. You understand? Okay, so this is called fractional band gap generator. Why it is called fractional? Because by the fraction of we can generate something that is fraction of the band. Yeah, it can be reduced by some factor of R1 by R fraction. And if that is the case, the overall power supply that will be required to generate this band gap reference generator will be smaller than what we had in the original band gap generator. Okay. So any doubt?
Fine, sir.
Okay. If there is no doubt, this was the tutorial for week 10. Thank you for attending.
Sir, the transmission lines.